going to count it in. I can never tell what's going to count me in or not. Okay, somehow I do things differently, I guess, every time. I can't figure out what it is. All right, so I've got these two friends, and these two friends are carrying a 10-kilogram bag of feathers. And there's always this, like running thing. Which is heavier, 10 kilograms of feathers or 10 kilograms of books? What's the answer? Both the same, 10 kilograms. Anyway, I'm pretty sure at the correct stage of development, all three of my children have asked me that joke because they've seen it on YouTube or whatever, right? But we look at the mass, 10 kilograms. Doesn't matter what it is. It's a bag full of feathers, though, in this case. And if they're going to carry it at a constant height in a straight path such that their arms are both 30 degrees relative to the horizontal, like, oh my gosh, this is a lot of constraints. But we're talking like this is their arm, 30 degrees relative to the horizontal. Find the magnitude of force each must exert on the bag. And essentially, we're talking about what the lift force would have to be by these two people. But, if these two people were holding on to bag handles, or you can even imagine more contrived, they've attached a rope to the bag, we could talk about the tension in the rope. Or we could talk about just directly what's the tension in their arms, right? Like what's the force that they would have to pull on at this angle. So we want to draw, first let's give ourselves a reference frame. Maybe I'll throw a reference frame off in the margin here. Reference frame seems to me up, down, left, right is good. We'll call it up positive and down negative, and right positive and left negative, sure. Now the idea of static equilibrium, maybe we should address that beforehand before we go any further. To be static is to be unchanged. And to be in equilibrium means for everything to be balanced out. Same, I guess, in chemistry, right? In this case, we would talk about it as being a body. So in this case, the bag of feathers is the body. It's in static equilibrium. If it's moving along at a constant height, not going up or down, not accelerating in any direction, that would be a static scenario. All forces balanced out. And while we're going to talk about it in terms of carrying a bag first, this is something that's important for architecture. Anybody who's a civil engineer would ideally like every point in their building to experience static equilibrium, unless we're going to be thinking next level about how we're going to deal with earthquakes or structures that sway in the wind, that sort of thing, which of course is a real engineering issue. But for the most part, we first think about building our bridges, think about building our houses in static equilibrium positions. And so we talk about like floor joists and rafters and all that sort of stuff, holding things in place. This is an important thing. So we're talking about feathers here, but recognize it's not really about feathers. This is like the gateway to talking about civil engineering type stuff, where we care about stuff staying put. Anyway, we've got ourselves a mass. Makes sense that we do the easy stuff first. The easy stuff in this case, I think, would include talking about force due to gravity. And there's only one body, so I'm not going to call it like FG feathers or something like that. But it seems to me, and I'm going to do this in dotted line, it seems to me that there would be a tension force going off this way and a tension force going off this way in the person's arm. And I could call this one F2, and I could call this one F1. Notice that there's no normal force because it's not sitting on the ground. But of course I could say, well, F2 is going to have, now I'll do solid lines, there'd be F2y, and F1 would have F1y. And I don't even know if you're going to be able to tell the difference, but I'm going to try at least to do this in purple. Does the purple look like blue? I don't know, maybe I need something more pinky than purple. But anyway, we'd have F2x and F2y. And then again, and I think I'm going to be a little bit tight on space here because of the size of my diagram. We said that the arms are 30 degrees relative to the horizontal. Now here I am drawing 30 degrees relative to the horizontal here. And people say, well, the hands aren't down there, the hands are up top. Let's just make sure that we know why that's 30 degrees. You know that if this is the person's arm reaching down at an angle 30 degrees below the horizontal, then there's a Z pattern thing going on, right? Yep.
There's, don't you mean F1x instead of F2y?
Oh my gosh, thank you for, you're right. This isn't F2y, that's F1x. Thank you. Here, I thought you were going to ask me a question about Z pattern. F1x. All right, so the reason that we can say these guys are 30 degrees is because, yeah, the hand is acting 30 degrees below the horizontal, but that would also be 30 degrees. Okay, so just a little bit of rationale on that one. So we've got all of our things labeled up here. And since this is static, I'll just make sure that, make a note, because it's static, or I could say since static, F net x equals 0 newtons, and F net y equals 0 newtons, because that's what it means to be static, not accelerating in any direction, up, down, left, or right. Net force is 0. I can say, okay, a little bit more thinking before I even start being a problem solver. Autopilot thinking says that F1x is going to be equal to F1 times cosine of, we could call it theta 1, but in this case we have a symmetrical situation. Theta 1 and theta 2 are both 30 degrees. F2x equals F2 times cosine theta 1. Now really I should be careful about this. We said to the left is negative. So really and truly the way that we defined our terms, I would have to throw in a negative sign right there in front of the F1, because F1x is pulling to the left. There's not a way mathematically other than human recognition or situational awareness to know that that negative sign is going to come in there. It's just not going to automatically pop in for us. Okay, so that's got to be forced in there. So I did it in red just so that we can say, yeah, look, we got to acknowledge directional positives and negatives. Other things that we know sort of are playing in the background is Fg is mass times acceleration due to gravity. F1y, here I was trying to be color coding about this. F1y is F1 times sine theta 1. F2y is F2 times sine theta 2. And somebody's going to say like, oh, which one do you have to put a negative sign in front of for those guys? Well, neither of them, because aren't they both pulling upwards, right? However, force due to gravity, if you really want to push it, I guess force due to gravity is negative. Yeah?
For F2x, would these theta be theta 2 instead of theta 1?
Oh man, you got me again. Now they happen to be the same theta this time, but yeah, for notation purposes, you're totally right. That guy should be a theta 2. I'm glad I have people to proofread me. Alright, so just sort of block this off for ourselves, keep ourselves organized, and I want to be an X thinker first. So in my X thinking, I'm going to conjure up a free body diagram equation. Of course, everything that's going in the X direction is equal to F net X. So F net X is equal to F1x plus F2x, which we said we should really write as negative, I'll put it in as a red just to make sure that we know that it's there, negative F1 times cosine theta 1 for Jake plus F2 times cosine theta 2. And there are purists out there that say, hey, if I'm going to call this negative F1 and negative F2, shouldn't we just like really draw attention to the fact that these guys are absolute values? And to that I say, yeah, sure, fine. If you didn't put the absolute values in there, I won't be upset about it. But just, yeah, we're just talking about the magnitudes, okay? The negative sign is going to get forced in there to talk about the directionality. Now I know this guy here was 0 because it's static. So the easiest thing to do here is to take the negative term over to the other side, and that makes it into a positive term. F1 times cosine of theta 1 equals F2 times cosine of theta 2. And at the end of this, we kind of get like this trivial situation, because since theta 1 and theta 2 are equal to each other, because this is a situation that's symmetrical, something really convenient happens. If they were not equal to each other, we couldn't do this, okay? So if one person was taller than the other, then I couldn't just say, oh, they're equal to each other, so we can do this canceling. Look, cos theta 2, cos theta 1, if I divide both terms by cos theta 1, those guys are going to cancel out. But if the thetas aren't the same, I can't do that, okay? So if I had one tall friend and one short friend, this wouldn't be a possibility for us. Okay, so that's why I kind of carried it out to the blue there, because the blue equation is something that I could use in an asymmetrical situation, but in this symmetrical situation, all we've really proved is that the magnitude of F1 and the magnitude of F2 are equal to each other. Which might be useful, actually. So I'll call it equation 1. Now, if I think about y information, my y information, slightly more stuff going on here. I can say f net y is equal to f1y plus f2y plus fg. If I expand this expression out, I can say, hey, f net y was equal to 0, so I guess I can just write 0 equals. But f1y, we already did the thinking on this one, is f1 times sine theta 1. f2y, f2 times sine theta 2. And fg, I guess we could write as that, we'll throw in the negative sign now, because we threw it in the list of formulas up above. Mass times acceleration due to gravity. But I might also make the little note to myself. C equation 1 and theta 1 equals theta 2 simplify. And if I do that, what I end up saying is, and again, you can't always do this. This is because it's a symmetrical scenario. When it's not symmetrical, you can't do this. It doesn't simplify out like this. And we'll do a non-symmetrical scenario in a couple minutes, but I want to show this one first. If the f1s are the same, that's what equation 1 says, and the thetas are the same, I could just write this as f1 sine theta 1 plus f1 sine theta 1 minus mag, because I'm acknowledging that those 2's can be replaced with 1's because of this statement right here. And then I can say 0 is equal to 2f1 sine theta 1 minus mag, take the negative sign over to the other side, mag equals 2f1 sine theta 1. If I wanted to get f1 all by itself, I could say f1 is equal to mag over 2 sine theta 1. Somehow that makes me feel like a trig identity, but it's really not at all. And I can just sub in my values. So I've got, well, the mass of feathers was 10 kilograms. 9.81 meters per second squared divided by 2 times sine 30 degrees. Now, the nice thing is, whatever this F1 is equal to the F2 because of symmetry. That means that when we find this F1, according to equation 1, we've also found a force 2. So what do people get for F1? Should be a nice round number, by the way. What's sine of 30? It's one of the magic numbers, isn't it? What do we get? Sorry? 20? I don't think it's 20, is it? No, it should be 98. 98.1. Sine 30 is equal to what? Everybody know? 0.5? 2 times 0.5 is 1. So that just clears the denominator out to make it be 1. 10 times 9.81, 98.1. Okay? 98.1 newtons. And then we could just say sub into 1. I mean, I know I already said it out loud. Sub into 1, but when we do that, we just say F2 is equal to 98.1 as well. Okay? And of course, yeah, we could write a therefore statement. Therefore, the tension in each person's arm is 98.1. But you know, it doesn't take a whole lot to change this thing. This is the special case for symmetry. We can make a lot of little, cancelings and subbing ins and whatever. But if you just change it a little bit, if you have, this is, what's this person's name? Did I give her a name? You know, I think in the original textbook that I stole it from, they called her Little Susie. Anyway, if Little Susie was hanging from a rope, but not at the center, you can see that the angles that we were talking about, those angles there and there, wouldn't be the same angle. And since they're not the same angle, what we did way back in the X thinking wouldn't be able to simplify in that way. And so we actually would have to hold on to like this guy here as our equation 1, and we'd have to hold on to this guy here as our equation 2. And if we had those two as our equation 1s and 2s, it's not like a simple linear equation scenario. It's actually a 4-variable trigonometric system of equations, but we totally could still do it. We know theta 1 and theta 2, we could sub them in, and then once we sub it in, then it becomes linear, right? Because the sine theta 1 and sine theta 2 would end up just being numerical coefficients. So it would still become like a system of 2 linear equations. It's just that it wouldn't be quite as like tidy as the way that we did it. So I did preserve my equation 1 and equation 2, just so that if you're in the future doing homework where it's not symmetrical, you kind of got those set up for you, okay? Yep.
Equation 2 needs to be the one on top of it, so like not sine 1 plus not that.
Sorry, say it one more time.
Wouldn't the equation 2 need to be the one above it? Because
Oh, you're right. It would have to be the one above it. Because you're right. You're right. Because we already plugged in the ones. Yeah. He's right. That would have to be equation 2 before we do our simplification. But I did still set us up for success for asymmetry. So I think we're good that way.